Here we have a pretty difficult geometry problem using circles. Two real numbers a and b are chosen independently and uniformly at random from the interval 0 to 75. Let O and P be 2 points on the plane with OP equal to 200. Let Q and R be on the same side of line OP, such that the degree measure of POQ and POR are A and B respectively, and OQP and ORP are both right angles. The probability that QR is less than or equal to 100 is equal to m over n. Find m plus n. So let's organize our information first. We have O and P. So this is O. We have a line here to P, and this is length 200. Q and R are on the same side of OP, so we can have Q there and R there. And we need OQP and ORP to be right angles. And this angle are A and B, which are randomly chosen from 0 to 75. So in other words, we have a 200, and we can draw whatever line we want here. It can be anywhere. It can be very close to 0, it can be very close to 75. But we have some point Q, and it makes a right angle here, and another point R in that range that makes a right angle there. We want to find the probability that the distance between Q and R is less than 100. Well, the first thing that should immediately come to mind is that we have O and P are the same base, and we have Q and R are both make right angles with O and P. So they must lie on a circle with OP as the diameter, since they make right angles. Yes. So we can put Q. This is 90, so let's say this is about 75. So it can be anywhere from 0 all the way to 75. So I'm just going to put Q here for now, and R here for now. That is nice. These are right angles. Okay, but how does that help us? Well, we need QR to be less than or equal to 100. Let's think about what happens if they are 100. We have a circle, and we'll put OP again, and we can put Q very, very close to P. So let's just basically put it on P. We want it to be 100 away. So it goes to some point here, that's R. And we'll say this is 100 away. 200 away, circle. If you split this here in the middle, you can see that half of 200 is 100. Or in other words, the radius is 100. And R is on the circle, so we can connect there and make another 100. So we have an equilateral triangle here. In equilateral triangles, we know these are all 60 degrees. So what does that tell us about OP and Q? Well, if it was 100, well, the central part must be less than or equal to 60 degrees. And since they go all the way out here to O, this is the central angle, and this is on the circle, so by the inscribed angle theorem, this must be half of that. So this is 30 degrees. So as long as the difference between A and B are within 30 degrees, then it would be less than or equal to 100, because if it's exactly 30 degrees, then the central angle makes it 60 degrees, and we have an equilateral triangle that makes it 100, 100, 100, and 100 is the highest thing we can make it. So now, given two numbers chosen between 0 and 75, what's the probability their difference is 30? Here we will use something called geometric probability. Because they can be chosen anywhere randomly here, let's draw a chart. This is A, this is B. We'll do 15, 30, 45, 60, and 75. Say this is 15, 30, 45, 60, 75. And we'll do 15, 30, 45, 60, and 75. If A is 0, B can be up to 30, so anywhere in here works. If A is 15, B can be up to 45. If A is 30, B can be up to 60. If A is 45, B can be up to 75. And if A is any bigger than that, well then B can go all the way up to 75, but B can't go any bigger than 75. So that's our limit. We have this part here, and we have this part here. B can also be less than A. So if B was less than A, it must be greater than 0 because it would be 30 away. If A was 45, B must be greater than 15 to maintain that distance of 30. If A was 60, B must be greater than 30. And if A is 75, B must be greater than 45. So we have this weird shape here, and it must be within this region right here. How does geometric probability work? We find the area of this region, area of the shaded, divided by the area of all possible, so total. The total is easy. We have 75 here and 75 here. To make it easier, we'll call this every 15, we'll call a length of 1. So the square has a length of 5 and a height of 5, so the total is 25. What's the shaded region? We can take the whole thing and subtract off these triangles. This triangle here has length 1, 2, 3, and height up to 45, so it's 15, 30, 45, that's 3. And this one also has 3 and 3. So we have 2 of the same triangles, and their length times width divided by 1/2. These cancel out. So the area of these triangles is 9. So the shaded region, 25 minus 9, 16. 16 over 25. That is our final answer. You see, in this rather difficult seeming problem, we used both the fact that we used inscribed angles, but especially the fact that the right angles are formed when there's a diameter. And furthermore, geometric probability, that's an interesting concept here as well, where you find the probability based off of what percentage, what ratio of the areas work.